good evening. I'm really delighted to welcome you to our Raspberry Pi Foundation Computing Education Research Seminar. I'm Jane Waite, and I am, as always, incredibly excited and delighted to be chairing today, and as I said, our 50th seminar. Since we started these seminars in 2020, we've really been so lucky. We've had such a privilege to listen to researchers and being able to connect with all of you people from across the world, educators, learners, researchers. And we just want to say a huge thank you for you taking part and also for your feedback. This year we've been focused on the theme of teaching programming, mainly with AI, but we have had a little bit of without AI. And I'm really pleased to say that next year, so we're going to, this is our announcement for next year in 2025, we're kind of following the same trajectory, but this time we're going to be talking about, or we're going to be having researchers talking about teaching about data science and AI, and more details will be shared on the website soon. And we have some fantastic people lined up. Today, we're very excited, very, very pleased that Nicholas is joining us from the University of Virginia. He's a PhD student in the Systems and Information Engineering department. And his research focuses on how people interact with AI-based code generators. And we know that that's something that's happening in undergraduate and is already starting to come down into schools. And so it's really important for us to start to consider this. And Nicholas's work is looking at how we can kind of guide them, the responsible use of this technology in CS education. So Nicholas is going to be discussing how AI tools like GitHub Copilot are changing the way that beginners learn to code, particularly under pressure. And he'll share insights from his recent study on the effects of these tools on coding, performance, workload, emotion, and self-efficacy, because I just read it off the slides. And I think it really is a timely presentation. So Nicholas, thank you so much for joining us, and over to you.
Thanks for that introduction. I'm excited to share this work with you guys. This research is a laboratory study about novice programmers using AI code generation and trying to make sense of what happens when we put students into that situation. I co-authored this paper with Dr. Raymond Pettit and Dr. Sarah Riggs, and I'm coming to you today from Louisiana, Virginia in the United States. So thank you for having me. So to get started, we probably a lot of us know that AI is really good at simple programming tasks. This example, I asked ChatGPT, back an older version of ChatGPT, about writing a Python script to add up some numbers. And the code it produced on the right in the first try is clearly quite convincing. It's well documented. It uses standard library functions. It has error handling. It's everything you would want to see out of a student writing a code for this particular problem. And more novices are getting access to high quality AI for free. You have chatbots like ChatGPT, Google Gemini, and Microsoft Copilot. You also have code generators like Amazon Q Developer, which you may have also heard of as Code Whisperer. And then you have some open source and other free options. There's Tab9 Basic, there's Continue.dev, which I'm going to talk about a little bit later. And Meta even has open source models that you can just download for free that generate code. And one of the artificial intelligence-driven development environments, you'll see that AIDE term I may use a little bit throughout this presentation, is GitHub Copilot. And Copilot is currently available for free to verified students, teachers, and open source maintainers. And GitHub themselves will call this something that can help you learn faster and code better. But we wanted to see some of the aspects, is that really true? And what can we find out by placing students with GitHub Copilot? So this is the AI that we're using for this particular study. We all have the concern AI isn't going to do students' work for them, right? Surely there's a protection in ChatGPT that will prevent it from students getting their homework answers from it. And you see here, right, it says, however, I cannot complete your homework for you. So surely we're safe, right? Unfortunately, even some of the early research is showing that AI is perfectly capable of taking your homework prompts and turning them into usable code or solutions for your homework and whatnot. So here you see that I've taken an actual University of Virginia course assignment, and I've just taken the context into GitHub Copilot as text, and then it's going to help me to write code for that problem by taking in that context and helping me to produce a good solution. So it's quite easy, and there's been research showing that AI definitely can solve these simple problems, and it's clearly easy enough to be done. But we wanted to know what happens when you take a student and you give them AI, and especially when you put them under time pressure. Because if you think about students doing their assignments with AI in the real world, what are they going to be doing? They're going to be trying to turn in their homework assignments or their tests, different things that put them under time pressure. And they might not necessarily act the same way when they have all the time in the world as opposed to when they're under a deadline. And at the time, there's really limited research looking at the quantitative effects of humans working with AI code generators in general. We're only aware of 3 studies at the time of writing this paper, and of those, only 1 study showed that participants had a significant performance benefit from using the AI code generator. In other words, it helped them to be more productive in their coding tasks when they had it, which it might be surprising to you given that it kind of seems common sense that it would help you. We also see some vaguely positive effects on the human side, things like being slightly less stressed or more eager to continue learning. Participants finding Copilot helpful compared to the last generation alternatives. Neutral and positive experiences using AI code generators. So we wanted to see what are some of the more measurable, validated things that we can observe when we put students under these conditions in a laboratory environment. So specifically, we wanted to look at performance, how productive are they at writing code, workload, how much are they engaging and how difficult is it to write the code, emotion, how are they feeling, and then self-efficacy, how do they think that they performed, and hopefully we can translate that into how do they think they might perform in the future as well. Our research questions were, research question 1 is essentially when we compare a solo programming task to a programming task that's assisted by AI, how does performance, workload, emotion, and self-efficacy change? And then with research question 2, we want to see if we can have students program more over the course of the experiment. Do we see any changes in performance or self-efficacy? To do this, we recruited 17 students from a Computer Science 1 course, Intro to Programming in Python. And we consider all of these students are generally novices, although on the day of participation, 6 of them did identify as intermediate on the scale of novice, intermediate, advanced. And we see that participants generally identified as female and Asian, although we did have representation from different groups. And the tasks that the participants were working on come from the human eval dataset, which is a very commonly used benchmark dataset from OpenAI. It's essentially when a producer of an AI model wants to evaluate its ability to write code, they often take this benchmark and run it to see how well the model performs. So we adapted that so that instead of an AI alone working on these tasks, we could have a human working on these tasks with the assistance of AI. To do that, we took the 164 tasks from that data set, and we had 9 human raters who were staff of a Computer Science 1 course from which the students were actually recruited. They helped us to examine some of these tasks, run through the tasks, evaluate whether students were going to be able to do these, how hard or easy were they, did they require any special knowledge? And from that, we organized 4 groups of task pools for our experimental design. Generally, we're aiming for this difficulty profile. So what this says is that earlier tasks within a pool of tasks would be on the easier side, they would increase in difficulty, and they'd be a little easier at the end. The reason they're a little easier at the end is that we want to throw in tasks that might require special knowledge, like, for example, a trigonometry function or some other knowledge that isn't necessarily computer science knowledge, but that a participant might not have. So we didn't know that these difficulties would be perfectly exactly, a 4 out of 8, for example. But we wanted to know that across the 4 task pools, we would see a similar profile, and that becomes important when you start to do the data analysis later on. We used within subjects design, which means that participants worked twice alone and they worked twice with AI assistance. So you can see 2 examples of 2 participants where they might have AI first twice and then without twice, or it could be spread out. And the order of the task pools could be counterbalanced across the participants so that we don't have them all doing the same type of treatment. And to measure the variables we were interested in, we used repeated measures over the 4 trials. So we would take an emotional affect measurement before and after, and then we would take an ordinal performance score of the task that they were working on during 20 minutes. After, they would also take a self-efficacy assessment and a NASA task load index, which is a way of measuring their workload. They worked in Visual Studio Code with a text editor you can see in the middle, a PDF description on the right, ways to test their code either through a point-and-click interface or the terminal. And they also had ways to see the time remaining and submit questionnaires, submit the tasks, and so on. They were given lots of training on this interface so that they were ready to go when the actual measured part of the experiment began. It's also important to note that the PDF encodes the description of the problem in a way that the AI did not have access to unless the participant specifically introduced it. So we're sort of seeing, without any particular instruction, are participants able to utilize the AI to their benefit? Because the AI itself cannot see the problem description. It can only see, as you see in the editor in the middle, it can only see the function definition and the fact of what it takes in as parameters, but it has no details on what that function means other than the name. For the score, we scored our task pools ordinally. So for each 20-minute trial, participants had the opportunity to complete as many as 8 tasks, but they had to complete 1 task before moving on to the next. So for example, in task pool B, you can't move on to task 19 until you complete task 54 and 53. And if you were on task 71 when the timer ran out, then you don't get credit for that one because you haven't yet passed all of the tests. Only the ones where you've passed all of the provided tests from the data set would you get that counted. So in this case, you would have a score of 5, even though you had completed 5 tasks plus a partial 6th. For workload, we use the widely used NASA task load index. This is a common way of measuring someone's physical, mental, and somewhat emotional workload. And we made sure to explain this scale to participants and make any counterintuitive parts of it very clear to them. So you can see on the left, we're asking about their mental demand, their physical demand, their temporal demand, which is essentially how rushed they feel, their performance, how well they think they did, and their effort and frustration levels. For emotion, we use the circumplex model of affect, which is a fancy way of saying, how did you feel positively or negatively, and how intensely did you feel that way? So we made sure to explain this to participants and give them Likert choices that align with this chart. So for example, high valence but low arousal would be a calm emotion versus maybe a low valence but a high arousal could be upset. And in terms of the data here, we didn't want to just measure emotion on its own because you could imagine that somebody's emotional state might be affected by things other than coding, right? Like something happened to them during that day that was different from other participants that we looked at. So we were actually comparing emotional state from before the programming trial to after the programming trial with a simple difference. And then if you have an AI trial and a solo trial with different emotional effects, then the idea is that you would be able to see how emotionally different is the experience of programming with AI assistance versus without it. For self-efficacy, we made a very critical assumption. Now, self-efficacy is a very hot topic in computer science education because you want students to feel like they're going to be able to succeed in the future, to push through some of those harder points in that education process. So the assumption that we made here is that if a participant notices that they've performed well on something that they just did, that they might feel they would perform well on something similar in the future. And the reason we have to do that is because we want to see what is the effect of this programming experience on their self-efficacy. So to make sure we really distinguished that from the effect of, how well did the AI do, we want to know how well did the participant think that they themselves did. And so while we're taking this measure that's outlined in orange, we also had them fill out these other questions about how well do you think the AI performed, and how do you think the work was split between you and the AI, so that when they're giving this self-efficacy measure, we can be sure that they're providing an answer about how well they themselves performed. With statistics, we took a conservative approach here because we have a small number of participants. So the main takeaway here is that we used the least conservative test that we met the statistical assumptions for. So you can find more details about that in the paper, but essentially we're just comparing the values that we're interested in from trials without AI to trials with AI. And I've tried to summarize these results as simply as possible. So when we compare the trials alone versus the trials with AI assistance, the text descriptions on the right describe the trends that we observed in these variables, but we've only bolded those which were statistically significant at the 0.05 significance level. So you see that in general, things are becoming easier and the participants are performing better when they have AI assistance, which may or may not surprise you. But the only results that were statistically significant were an increase in performance and a decrease in mental workload and effort. When we come to the second research question, to remind you, we were looking at how does the performance and also the perceived performance, that self-efficacy measure, how does that change from the first trial with AI assistance to the second trial with AI assistance, or the same in the solo trial as well. So what you can see is that from the first solo trial to the second solo trial, we see no change in performance. We also see no change in the participants' grade of themselves. So that is essentially they're not improving, they're plateauing, and they're noticing that they're not improving. However, when they're with the AI, they do improve by about 1 task out of a possible 8 between the 2 trials, and they're also noticing that improvement. And I'll remind you that because we measured also how much they think the AI contributed to that we can feel relatively confident that they're actually attributing this performance benefit to themselves and not to the AI. So what does this mean? First, I want to point out one possible confounding factor that is very relevant, which is internet access. So in our solo condition, participants did not have access to the internet. And this was an intentional design choice because we wanted to compare solo programming to AI-assisted and not internet-assisted to AI-assisted. But we will point out that in the previous research where performance has not improved, they have had internet access in the solo condition. So essentially, you might see that AI is subbing in for that internet access as the tool that's helping students to perform better or experience things more easily. However, there could be other explanations, so we can't be sure that this is the case, but we just want to point out that this is definitely a possible confounding factor. In terms of workload decreases, the 2 measures that we see workload decreases in are mental workload and effort. And these have been observed in the past to be the highest among workload measures in educational programming. So it's probably not surprising that these would decrease when you get an assistance. However, there's also been a small amount of research looking at how does learning relate or correlate to these measures. And in one particular study, when these 2 measures went down, learning also went up. So we're not saying that lower workload will improve learning, but there's potentially a path there, with the obvious caveat that if you're not engaging with the task at all, it's pretty likely that you're not going to learn much. In terms of the emotion, we also see both with valence and arousal and with the TLX frustration dimension. So that question asking about how frustrated did you feel while you were programming, participants are trending towards feeling more positive, more relaxed, and less frustrated, but none of those differences were statistically significant. So we don't have enough evidence to say that AI is going to make you feel better. And I think that was potentially something that we would hope AI could unlock, but I don't think we have the evidence to say that from our work. We also see, as I mentioned before, that novices don't take credit for AI's work. So even though they received a performance benefit from working alone versus working with AI, they are not attributing that performance benefit to themselves in a way that's statistically significant. That is, they're noticing that this improvement has happened, but they're saying, oh, it's because of the AI. It's not because of what I did myself. However, when we look at the first AI trial to the second AI trial, we see that performance improvement between those two, and we see an improvement in the self-grade. So they're performing better, and they're noticing that it's because of something they themselves did. So in conclusion, one of the concerns is the ecological validity of our study because it's in a laboratory environment. That is the strength of our work, is that we can be in a very controlled environment, but there's a question about whether that is really like the classroom. We have no internet access in the solo condition, which is not typically how students operate, and our sample size is relatively small and from one school. We also have tasks that could have potentially been in the training data for the AI that participants were using. So people have different thoughts about how much of an issue that is. But what we can say is, even if the AI is especially good at these tasks, there's only so much that the participants are able to kind of unlock that performance of the AI. So you can think about it like a ceiling on how well they could perform with an optimal AI. And I'll point out that AI is going to continue to get better over the coming years, regardless of whether the data is in the training set. Key takeaways are that novice programmers can be more successful with AI. They can think and try less hard, and they can improve over time and take credit for that improvement. However, they don't take credit for work that they attribute to the AI, and they don't necessarily feel much better using the AI. So what does this mean? Well, the temptation for using AI to code in an educational setting, it's definitely there. I think that's clear. However, there's not as much of a self-efficacy or maybe a benefit on the human side as we might have hoped to see. So potentially, if there were some concerns about giving students AI access and these benefits could justify it, we don't necessarily have the evidence to say that at this time. However, in terms of the improvement on the AI trials, we see that students are needing to learn something. So as Jane and Bonnie were mentioning earlier, it's very important to teach students the skills to collaborate with AI, because we've shown in our study that they don't have those. They're not at maximum performance right away. Even within the span of 2 40-minute sections, they're improving over the course of that time. So what that tells you is that they did not come in with the same skills into the experiment that they left with. And so there's definitely something to teach there. And as they improve in those collaboration skills, they're going to get better at working with AI and better at holistically coming with good outcomes from their programming endeavors. So they're going to notice that they did better and take credit for it. And we hope that that's a path for them to build self-efficacy by saying, hey, I did better in prompting this AI to help me write code. You know, it's something that's different from what self-efficacy looked like 5 or 10 years ago, but it's still potentially something that's going to keep students interested in computer science and pushing through those difficult times. And here's the full citation and some of the people that I'd like to thank for helping with this work, as well as my contact info and website.
So if we can give a big thank you to our speaker, give him a virtual round of applause. So our next seminar is going to be in December. What date is it? 10th of December. I'm really excited, but Leo Porter is going to be here. He's done just so much research in this area. We're very excited to have him coming along. He was due to come earlier in the year, but he's had to come later. So please do join us for our final Christmas kind of celebratory, that we have 51st research seminar with Leo Porter, and have a lovely evening. And thank you again to Nicholas for sharing his research.